Hello, everyone. We are going to do a demo of what Intelligence has done as part of the Sandbox, FCA Sandbox evaluation and the kind of data that is available there. So we kind of conducted an experiment, set of experiments, but we are going to talk about one of those experiments, which is related to app fraud detection using large language models. So I've just launched that digital sandbox here and logged into the Sandpit environment. So this is a Jupyter notebook which contains some of the experiments that we have done for this use case. So the idea was to use the app fraud detection synthetic data which was available in the sandbox to basically fine tune a pre-trained large language model in order to be able to see whether it can provide predictions with a good accuracy and also talk about some of the explainability around the predictions. Okay, so that's the summary. We basically used open source large language model in this case, and we utilized part of the data that was available in the sandbox environment. So specifically for app fraud, there were millions of records available, which we actually selected or kind of selected certain attributes and only a subset of the data, which is around 42,000 transactions, which are related to app fraud. Uh, and this data belonged to 5 different banks. There were personal transactions and fraud-related data in this case. And so just to provide a summary that once the model was fine-tuned, it was basically tested with around 70,000 different transactions, out of which we saw results where 0 transactions were where fraud is classified as not fraud. There were 70 transactions identified as fraud correctly, although the type of the fraud could have been more accurate. And there were 12 different transactions where not fraud was actually classified as fraud. So now I'm going to talk about some of the sample scenarios that we have listed down here. So we have um, a Python web application running in the background for which this is the REST endpoint. So, and then we can provide different prompts to the LLM through this API and see what are the predictions made. So just before this demo, we are kind of run all of these different cells so that it doesn't take much time during the demo. But we can see here that this is a 2 positive prediction case where LLM has predicted advanced fee delivery customs as the fraud classification, and it matches with the actual data uh, actual label or classification for that personal transaction that was there in the data. So just to note here that none of these verification data sets that we have used was already seen by the LLM. It has been all the inference has been done on new data which the LLM has not seen before. So this is the prediction made by the model, which is identified as a fraud case, and for fraud categories, advanced fee delivery customs, which I have also mentioned before. We have also thought about generating some similarity search results, which means that we want to identify similar transactions which were there as part of transaction history data. So we are using a Milvus DB there, which is a vector database, which can help us identify similar data. So there are a list of transactions which are truly or are the most matching cases with the transaction data that we have supplied to the LLM in this case. We can go through these results and see whether, for example, here I can see that most of these transactions which were there earlier, they were actually advanced fee delivery customs, and the fraud classification was true, which is also matching with the prediction that LLM has made. Also, we have kind of done the explanations. We have utilized a tool which can provide black box explainability for such a model. And here we are just providing that output to explain what are the predictions about. The first section basically provides a likelihood of a certain classification for this transaction. In this case, for example, the Lime model is saying that the probability or the likelihood of advance fee is 93%, which is the highest, and that's why the LLM, and we can link that with the LLM prediction as well, which says the same matching prediction. Also, the Lime output specifies what are the feature weights associated, what features in the input of the data that we supplied to the LLM actually contributed positively or negatively to the output, which is listed down here. And this is just a graph of the same data that we have here. We can see green graph points are basically relating to positive influences related to, let's say, the merchant name, narrative, the type of transaction category, and the red influences are basically negative feature weights which are associated with the prediction. So similarly, we have other use cases where we have a true positive. So this is a true positive case where the balance in the account was subsequently set as 0 after the transfer was made. So LLM has correctly identified it as an impersonation of the bank. And then there are similarity and explainability metrics over here. You're going to talk about one of the other use cases where we are seeing a behavior where the LLM can, let's say, for a similar transaction, but for same merchant, but two different transactions are giving two different behaviors. For example, this is a true positive case, the first one, where LLM is detecting this as a purchase scam, which is correctly identified in the data. But just the change in the type of the transaction to shopping clothing is resulting in a different prediction, which is it's not a fraud. And this is also this is actually a true negative case, but it's a correct prediction by the LLM model. Then we have a set of results over here where we are, because we have 70K records used during inference, so we have shown this confusion matrix over here, which says that there were all the fraud cases which were there in that data set, 70, were identified as fraud. And there were certain not fraud cases which were there in actual, but they were identified as fraud. So there are 12 such cases only in the total data set of around 70,000 transactions. And there were no cases where a fraud was actually not detected or was detected as not fraud. So most of the predictions, I would say, were correct. And this is basically the last number is 69,000 something, which is all of the not fraud transactions were actually correctly identified as not fraud. We can see here that a large amount of data is categorized in the actual data set as not fraud. And this is kind of a scenario which is very standard in fraud cases or anomaly detection cases, because there is very limited amount of data in a real world which could be identified as a fraud or labeled as a fraud. So this is a true reflection of that as well. Then we have shown some of the results for the cases where fraud was identified correctly, but then the category of the fraud was a bit misaligned. It was not correctly categorized in the right category. And we have provided some of the reasonings that we have thought about, because we have exposed this LLM to a data set which is not very large, only 70,000 transactions. But in real, if the LLM could be exposed to a very large data set, it could provide higher accuracy. Also, that where we have seen in this particular data set of 70,000 transactions that there's a data imbalance, which means that in this example, the impersonation categories have very limited data. So that has also led to some of these results. So that was about the experiments that we conducted and what were the results. I think this was a good showcase of how LLMs could be used in practice with very minimal data set as well to get reasonably good results. But then, of course, we have some future work in mind, which involves exposing this, fine-tuning this LLM based on very large data set or extended data set, doing further feature engineering, feature selection, things like that, traditional machine learning approaches that we can follow. And we are thinking about implementing retrieval augmented generation, which is RAG-based approaches to enhance the contextual understanding, incorporate dynamic learning and increase explainability of the model during inference time itself, which is one of the very latest and this state of the art approaches in deep learning. That's all for today. Thank you.